introduction about the Thin Film Society and the coming conference. The Thin Film Society is a professional society dedicated to the art and science of thin film and coating for their myriad applications, established for the world thin film included from academic researchers to industrial participants, and from material equipment suppliers to product designers. Though formally established only in 2009, the Thin Film Society is also the de facto host of the highly successful and visible international conference on the technological advances in thin films and surface coatings. The biannual Thin Film Conference series started in 2002 with about 70 participants and exponentially increased to more than 300 2 years later. 500 at Thin Film 2008 and 2006 and 800 at Thin Film 2008, and maintained at around the same level in the last conference Thin Film 2018. The 10th conference was scheduled in 2020 but has been postponed due to the COVID-19, and now it's rescheduled to be held in 2024 in Singapore. We expect an overwhelming response and record high participation in the event. And the 10th International Conference on Technological Advances of Thin Film and Surface Coating will be held on 15th to 19th July in this year in Singapore. And welcome. For us, we are the Organic Electronics and Photonics session, which is held by Professor Xiaoyan from Shandong University and Professor Yoshida from Chiba University and Professor Wu Hanyong from Korea University. The submission deadline of the abstract is on 5th February in this year. For the scope of this session is highly interdisciplinary and crosses the boundaries of physics, chemistry, material science, and optics, and will address fundamental questions as well as applications. Topics of interest may include, but not limited to, the organic electronics and the organic photonics. Other topics related to perovskite and hybrid organic inorganic materials and devices, etc. So welcome to join the Thin Film meeting in this year. And next, I will give a short introduction about the first reviewer of the first. Okay. The first one, the speaker is Professor Du Xiaoyan from Department of Physics, Shandong University. And her title is Morphology Control for Surprising Degradation of Organic Solar Cells. Okay, Professor Du, I think you can start.
Okay, thank you. Thanks for the introduction. Now I will share this, share the screen. So can you see the screen?
Yes, yes.
Okay, thanks. Thanks for the organization, and I'm very happy to have the opportunity to talk here for the Thin Film Society webinar series 14. And my talk is about the morphology control for suppressing degradation of organic solar cells. Here is the outline. First, I will talk about the aggregation control for photostability of a series of non-fluorine acceptor materials. And then I will talk about the morphology stability considerations for the solar cells. Firstly, let's look at this example and see what can we learn from these very stable organic solar cells. This solar cells is from fabricated by thermal evaporation. This is the photoactive materials. And in this data, we show we see the photodegradation, photostability of the cells under different levels of concentrated light. And even under 37 concentrated light, compared to the standard one sun intensity. This kind of solar cells still remain close to 90% efficiency after around 1,000 hours illumination. And if we extrapolate the operational lifetime, it's extremely stable. And so what makes the cells so stable? We can divide these aspects into three about the photostable materials, the morphology, and the interfaces. About the stable materials we see here, the authors commented that C70 is used instead of C60 because this can suppress the photo-induced isomerization. And these materials, they have very high bond dissociation energies. And also, due to the evaporation, the materials are also purified. So they have very high purity in the active layer. About the morphology, this kind of material, they have bulky conformation. This will be helpful for inhibits crystallization and increase TG. And due to the thermal evaporation process, the molecules are also able to form stable the mixing close to thermal equilibrium state. Of course, here we see the interfaces. It's also very it's also more or a little bit more complex than what we use in most of the solution processed organic solar cells. So we see there are many differences in this cell and what we are doing with the organic solar cells. Here in this work, we previously showed that the molecular engineering of the non-fluorine acceptors it's quite important for the photodegradation. And in the later slides, I will show you mainly the influences from these side chains in different kind of non-fluorine acceptors. In this work, we showed mainly how the device performance changes depending on different material systems. And in order to improve the photostability in general, of course, it's very important to have a deeper insight into the degradation mechanism from different levels. Here, this work I cited here shows the understanding on the molecular level, how the molecules degraded under illumination. In this work, the authors revealed the volume conserving photoisomerization of this end group in this position. And this photoisomerization will lead to subsequent photooxidation of the materials. And this is the way the material degraded. And in this work, the author showed that even without oxygen, this kind of materials, it can undergo this intramolecular 6E electrocrystallization and producing this kind of fused ring isomers. And this can happen without the presence of oxygen and only under illumination. And the triplet state is very important during this photo reaction. And for this, in order to understand further the molecular level and on the aggregation level, how the material stability is influenced, we investigated this different kind of non-fluorine acceptors. Here, they are differing in the core unit shown here. We call it M series, Y series, and IT series. We also changed the halogenation atoms at the end group. Here shows the result of the stability measured by UVV's absorption spectra. So we can see that both of the M series and the Y series, under the same condition, they show exceptionally stable properties compared to IT series. And this is related to the conformational stability of the materials or photochemical stability under illumination in nitrogen atmosphere without photooxidation effect. However, if we look at the lifetime stability of the excitons or the PL lifetime evolution under illumination, we see that all these materials, they show degradation in PL lifetime upon illumination. And this trend is not dependent on the core unit or the end group halogenation. So we don't see any reliable trend depending on the chemical structures. And we know that the exciton lifetime is probed here. It depends on not only the molecule, but also the interaction or the aggregation states of the molecules in the solid state thin films. So in order to look deeper into the degradation origins, we intentionally diluted this one of the material here using the polystyrene polymer. So we get two emission peaks. One is from the intramolecular excitons, and the other one is from intermolecular exciton. We can distinguish them by not only the peak position, but also by the temperature dependence behaviors. And for the stability we show here, the degradation in the exciton lifetime is mainly from the aggregated states, while the intramolecular exciton is quite stable. And these results correlate with the decrease in the exciton diffusion length as shown here in three of the materials. And this trend is observed in all the other 6 non-fluorine acceptors, including the other 2 M-series materials, and the 3 of the Y-series materials, and also the IT series materials. And also we see relevance of this phenomenon in the blend films with the commonly used donor material here. So this is quite a general phenomenon for the degradation of exciton lifetime and the diffusion length in the aggregated states. Although we are not quite sure now how to overcome this or what's the origin, we could think that the way to overcome this issue is to fast quench excitons in the DA components in the blend films. So fast quenching of excitons is not only important for the device performance, but also crucial for the photostability of these non-fluorine acceptors. Okay, now in the next slides, I will mainly talk about the morphology control for the stability of the solar cells. Previously, in this work, we discussed about the demixing in the mixed amorphous regions in these fluorine-based and non-fluorine-based organic solar cells. And we speculate, or we propose that the demixing in the amorphous region and the diffusion limit, especially the diffusion limited diffusion of the non-fluorine acceptors, is one of the degradation origins for this morphological instability. And the way to overcome this or to suppress this degradation is to increase for the miscibility or compatibility of the donor and acceptor materials, and also to suppress or decrease the diffusion of these non-fluorine acceptors, increase the TG for these materials. And for the TG, in this work, Professor Ho and Professor Harad, they showed that they investigated the thermal transition temperature of this a series of high performance non-fluorine acceptors based on this BTP and its derivatives. Here, the TG is measured by the deviation in the absorption spectra upon heating or annealing of the thin films. This is very sensitive method to measure the thermal transitions in the thin films. And also the thin films is it's close to the device condition. The result shows that all these BTP these analogs, they show a TG the thermal transition temperature below 100 degree, or some of them even show a low temperature at around 50 degree. So this is shows that for these materials, they are easily movable in the solid fields. And we also investigated one of the material shown here and compared the thermal stability with the polymer donor PM6 and the PYIT as the polymer acceptor, and compared with the fullerene derivatives. And we show that even under this transition temperature here, around 65 degree, we show that even at lower temperature, they show a higher slope compared to other materials. And this phenomenon, or this thermal transition behavior is obvious in many other optical-based measurement. For example, in this sensitive EQE here, this blends based on the non-fluorine acceptors shown here is easily changing or modified by thermal annealing, and also in the emission of the also in the electroluminescent spectral peak position. Based on the non-fluorine acceptors, it's easily or more readily modified. And this slide shows the reasons for decreasing VOC in the organic solar cells, actually. But I'm only talking here about the thermal stability of devices. In this work, we show that the devices based on this donor and this acceptor materials, they indeed shows very sensitive stability upon degradation under thermal annealing. Here is the room temperature device stability, and at 60 degree, it degrades very fast, and even faster at 85 degree. Using ternary or quaternary blends, this stability or degradation can be slightly suppressed. The reason can be seen from the GVAX. Here, this is for the binary under thermal annealing for different times, and here that are the quaternary blends for, under annealing for different times. From the quantified crystal coherence length, we can see that quaternary can slightly obviously suppress the changes in the crystallinity in this blends. So we can use multinary blends to enhance the thermal stability, but from molecular level engineering, how to increase the TG or increase the thermal stability of the of the small molecular acceptors. In this figure, we show that if we increase this side chain length, or if we make the side chain length shorter, the TG will increase. But this is in this result, or this guideline is contradicting to what is required for device processing with the scalable method. For example, here in this work, we show that if we transfer the fabrication from using spin coating with the toxic solvent to more scalable coating technique, including this doctor blading and more environmental friendly solvents. There are performance losses if we use shorter side chains here. This one is Y6, and here is with longer side chain in this position with N3. And this one is with this long LP side chain component Y6DT. And exactly this material shows a glass transition temperature at around 50. So the requirement for thermal stability and processing seems to contradict with each other. So we need to overcome this trade-off. The reason for this performance loss for materials with shorter alkyl chain is that in the halogen-free solvents, the solubility is worse, and the materials are easily aggregates in solution. So this pre-aggregation in solution will lead to this kind of morphology observed from AFM, and the features, disordered crystal orientation. All of these features, morphological features, are detrimental to the device performance. So another example we show here highlights the sensitivity or the need to have a wider processing window during coating for this non-fluorine acceptors. Here shows that again with the scalable blade coating method, if we only change the coating temperature, the drying kinetics is changing significantly, which again influence the crystallization here of this blends. And for the device performance, what we need is a medium state as shown here schematically. So we need to overcome or to suppress the over-crystallization of the non-fluorine acceptors in slow drying process. And we also need to suppress the over-mixing in the fast drying kinetics. But for the stability measurement, we need the uppercase that it favors more crystalline, more phase-separated crystalline domains. And for processing, we need to know that we need materials that is not so sensitive to the processing conditions, for example, the coating temperature and also the coating speed. So for materials development, these three aspects need to be balanced in order to improve performance, stability, and also the processability. Okay, so far I only talk about the non-fluorine acceptors, and what about the roles of polymer donor in the stability of the solar cells? Here we show an example that we use a planar heterojunction or bilayer structure here to investigate the influence of the crystallinity of the polymer donor layer for stability. This transfer printed PM6, the crystallinity is influenced or controlled by adding additives. Although the device performance is not high due to the bilayer structure, we can use this well-controlled morphology to study the stability. Here shows the thermal stability of these bilayer devices. The changes in the photocurrent, the GSE, and the fill factor under different annealing temperature reflects the intermixing of the donor and acceptor at these interfaces. And we see that if we have amorphous polymer layer, as shown here, the black curve, and we see faster decrease in the device performance, including fill factor, mainly the fill factor, and we see increase in the photocurrent because we have more intermixing and the axon diffusion is more efficient. So this is the result of the device with amorphous polymer layers. If we have more crystalline polymer layers, this degradation in fill factor and the increase in the photocurrent is suppressed, indicating that this interface is more stable. So we can stabilize the interface by increasing the crystallinity of the polymer layers. In addition, we also show that this interface with the solution processed whole transporting layers, here we use P.PSS, is also very important to the photo stability here. So the device with very amorphous polymer layers here shows very fast decrease in the photocurrent, and with the enhanced crystallinity, we see significantly enhanced photostability. So this degradation is attributed to the interaction of p-dot PSS material with the amorphous PM6. With this result, I think we can see that the crystallinity of the polymer layers if we increase the crystallinity, we can somehow lock the diffusion of the non-fluorine acceptors, and also we can make the interfaces very stable. Okay, now I come to summary. For the photostability of non-fluorine acceptors, we show that the intermolecular interactions in the aggregated states need to be stabilized. And this degradation in the intermolecular interaction will strongly affect the exciton lifetime diffusion length. This also highlights the importance for faster exciton dissociation for stability, photostability of the non-fluorine acceptor materials. And for the morphological stability, the result shows that most of the non-fluorine acceptors, the TG is relatively low for in terms of thermal stability. But we also notice that there are more report about the oligomer non-fluorine acceptors, which increase the TG and also showed a very promising thermal stability. And as for the polymer, the crystallinity is crucial for both the morphology and interface stability. For the side chain engineering, we need to consider the trade-offs between stability requirement and processing towards upscaling. Okay, in the end, I would like to thank my collaborators for the works I talked today, and also students and postdoc who did this work. In the end, I would like to draw your attention again to the Thin Films conference in this year, which took place in Singapore in July. And Professor Hao and Yoshida and Professor Wu organized the session 9 about the organic electronics and photonics. And the abstract submission deadline is in February 15. So welcome to join this meeting. Thank you for your attention. Okay, I would like to ask if there are any questions from the audience in the chat or anywhere else. If not, I will then chair the next session. The next session will be okay, then if no questions, we will continue. So the next talk will be given by my colleague, Professor Yin Hang. He will talk about extracting charge carrier mobility in organic solar cells. Okay.
Okay. You may close the. Okay.
Sorry. Yeah. I will stop share. Okay.
Okay. So thanks, Professor Du's invitation, and hello. I'm Yin Hang from Department of Physics, Shandong University. First of all, let me thank all of the audience here. Thank you for your time and patience. So today I'm very happy to share our recent work named Extracting Charge Carrier Mobility in Organic Solar Cells. So first of all, why we do this work? The reason is because the mobility is quite important. Almost every paper so far will report the mobility values. And there are already some constants in the opioid field. For example, a balanced electron to hole mobility ratio, somehow corresponds to the desirable field factors in the high-performance organic solar cells. But if we only consider the principle, it seems that everything is perfect, no problem, right? As we already got the theoretical case to explore the performance of the electron behaviors in the backend junctions. But in fact, we still need to address a lot of problems before we can say we have get everything in organic solar cells from the birth of time to the final peak. So most of this work was finished by Jiang Dongcheng, my master student, a very good person, and the fundings from NSFC and the Shandong province. And meanwhile, we also need to thank Professor Hao Xiaotao, Du Xiaoyan, and Gao Kun from Shandong University, and Professor Ye Long, Jian Yu, and Professor So, Professor Li Gang, Professor Sun Yanming, and Professor Zhou Yingping, and Professor Wei Wei, as well as Professor Yan and Yuan Jun from Zhongnan University. Here is the outline of this work, and we will share our motivation and then some measurement analysis and the device fabrication process. So before everything, I may introduce my group first. And my group is doing some fundamental studies of organic semiconductors, especially the charge carrier transport analysis in the solution process organic materials. And also, we also do some defects analysis. And meanwhile, we're also seeking some new horizons for the application of organic solar cells. For example, the indoor PV, etc. So actually, in recent years, the development of organic solar cells is amazing, as the field already got many high-performance devices exceeding 20% efficiency. And the stability issue is also in the way. As just now Professor Du mentioned several years ago, the non-Fourier acceptor-based devices can reach an extremely desirable stability for say about over 10 years. So therefore, it's indeed a very suitable time for us to do some deep investigation to further push up the field of the organic solar cells. So in this work, we use some polymeric acceptors and some small molecular and non-Fourier acceptors and some Fourier-based counterparts. And for the other side, for the donor materials, we use a series of the donor materials from the PDB7 to the PDB7TH and the PBDBTSF and the PM6 and the D18 to finish this work. So to investigate the behavior of electron transport in organic solar cells, we need to compare the effects of the electron acoustic and electron-electron coupling. It means if they are comparable, the polar model should be dominant. And if we do not need to consider the electron-electron coupling effect, then we can use the Hoping model. And of course, so far, very few reports so far talk about the band transport in the organic semiconductors. And for theories, I think the Mach theory is very, very useful, as well as the quantum charge transfer theory and the dynamic Monte Carlo simulation is also a very useful technique. And for the techniques, actually, honestly speaking, the time of flight, the first one, should be the best, as what you see is what you get. 那么也就是我们所说的这个所见即所得啊。但是这个东西啊，我们搞 OPV 是不行的，because it's most impossible for us to get a 1000 nanometer active layer to measure the electron mobility for the non-Fourier acceptors. So that's the reason. So why in the early years, many very interesting time-of-flight works published, especially for the P3HT PCBM system. And another problem is the cost. because we do not have a lot of money to buy such a huge amount of non-fluorescent acceptors to get such a thick film devices. So therefore, the time of flight is good, but not suitable for the organic solar cells. And the admittance spectroscopy, the fifth one, I think is another alternative. So although we have many papers based on this technique in recent years, but here I have to say it's very difficult, as we cannot control the perfect ohmic contact in every electron-only device. So especially for some new materials, which we do not familiar with the physics properties. So the failure rate is very high. If you are not specifically study the mobility, do not use it further. So therefore, I think the derivation of the standard space charge limited current should be the only answer, still from the SCLC technique. So we can see a very interesting example. We just summary several typical bucket junction systems and compulsory fitting the mobility values. We just fit, do not confirm whether it's right or wrong. And we can see the result are quite different. So what is the real mobility and how to extract the mobility accurately? Because for the same JV curve, if you use the different models, you can get the difference even up to 1,000 times. It's very huge. And so far, actually, there are 4 types of the widely used space charge limited current models. They are named the MG model, the Rose model, and the MH model, as well as the PF model. And here, the slope of the current density as function of the voltage curve should be the key factor to distinguish the differentiated SCLC models, as selecting the appropriate model is very important to accurately estimate the device mobility values. Okay, from the very beginning, I think many papers just use MG model. The reason is the MG model is very easy, right? Because the physical mechanism, it means there's no traps or traps are already filled. So we can just fit in the relatively high voltage. But we cannot confirm every electron or hole-only device are trap-free, right? So the mobility values should be different. And other models, for example, the MH model or Poincare model can be also adopted in different conditions. And here it's very interesting for the Poincare effect because many people use the PF model to fit the mobility values. But we can see the G value is consistently increased. So sometimes we can get a huge error if we only consider the PF effects instead of the others. So therefore, how can we address this problem? Because for the standard SCLC model, there are a lot of ideal assumptions and exponential limitations during the SCLC measurement. First of all, there's no diffusion current, but how come we can confirm it, right? And then for the anode and cathode, for both the electron-only or hole-only devices, we have to confirm its ohmic contact. It's also almost impossible, right? And thirdly, the contribution of the injected charge of the internal electric field, we cannot consider it, right? So we just differentiated the electron-only and the hole-only devices, and we get the conclusion that we need different requirement for different kind of the single carrier devices, and how to get the relatively accurate mobility value. It equals the reasonable single carrier device structure plus the correct model selection based on the G value and plus the extended voltage measurement range. Usually, for the current organic solar cells, we have to fit it to the voltage larger than 4 volt. And then we just take the PM6 based BHG systems with various acceptors as examples, and we just combine the JV curves with the JV values. We observe it's really a powerful analysis approach for the analyzing the SCLC data. And we can conclude the coexistence of the high molecular weight polymers with the PF effect suggests a field-dependent transport model in these systems. That's the same for the whole transport. And then we cross-check the mobility values by different techniques. And we just used the admittance spectroscopy techniques and the dark injections with charge-limited current. We just performed them to verify the accuracy of the mobility values. And we can see the figure H, right? If we use the right model, for different techniques, we can get the very close zero field electron and hole mobilities, which means that after the cross-check for with different techniques, we can confirm the select of the fitting models of the SCLC should be right, or relatively right. And then we just study the interrelation between the molecular structure and the methodology. We can observe the electron transport is sensitive to traps, and a small variation can lead to the changes in the transport model, while the whole transport seems less sensitive to traps, which is consistent to the published reports. And the varying sensitivity of the charge carrier transport to traps between small moleculars and the conjugated polymers can be attributed to distinct charge carrier transport models arising from the molecular structures. We can see here the difference in the interpolated transporting network for electrons in the planes affected by molecular stacking of acceptors is key to distinguish charge carrier transport models. And then we just observe the field-dependent charge transport is necessary to describe the prominent long-range intra-chain hoping carrier behavior in polymers. In polymers, we always get the field-dependent Paul-Frankel effect, where on the other side, the short-range intermolecular hoping will usually result in the trap-involved charge transport model with the small molecular acceptors, just like the peptide stacking. And finally, based on all the analyses above, we just do some solar cells to confirm whether there are some real applications, and we observe with the synergetic, the intramolecular hoping strategy, we fabricate the thick film, the PM6 PYIT based all polymer solar cells, and with a very high efficiency. We can see here the 16.6. I think the efficiency is desirable. Okay, finally, let me show the conclusions. And first of all, we outline the common pitfalls in mobility extraction employing the SCLC measurements and propose practical methods to improve the reliability of the mobility extraction. And then we investigated the interrelation between the photovoltaic molecular structures and the methodologies for the SCLC fitting. And we observed it's very important that the field-dependent charge transport model, the Paul-Frankel model, is usually in the long-range intra-chain hoping in polymers, while for the small molecular acceptor models, we always use the MG or MH model. And finally, we based on the analysis above, we just get some the high-performance thick film or polymer solar cells. Okay, it's my talk, and thank you very much. Just like what I said just now, and welcome to Singapore in July. And please take the session 9, organic electronics and photonics. And the topics of the interest for this session may include, but not limited to, organic electronics and organic photonics, as well as other topics related to perovskite and hybrid organic inorganic materials. And okay, thank you very much. Thank you for your patience for all the audience. And let me stop here. And okay, that's all. Thank you very much.
Yeah, thank you.